Hidden deep within the Rocky Mountains of Colorado, one of the most ambitious and controversial construction megaprojects in the United States is quietly unfolding. Here, hundreds of thousands of tons of fresh concrete are being poured directly onto the crest of a 70-year-old dam to raise it by more than 40 meters. Right in the middle of a narrow canyon, nearly 2,400 meters above sea level. They spent 20 long years fighting legal battles and hundreds of millions of dollars just to secure permission to pour the very first batch of concrete. Welcome to Mandarin Tech. Today we're going to explore the Gross Reservoir Expansion Project, one of the most intense and high-stakes construction gambles ever attempted in the Rocky Mountains. Few people realize that much of the water sustaining the Denver metropolitan area today does not come from the eastern side of the Rocky Mountains, where the city itself is rapidly expanding, but instead originates from the western side of the range. For decades, Denver Water's Trans-Mountain Tunnel system has continuously transferred water across the Continental Divide, delivering it to reservoirs located much closer to population centers. Within this network, Gross Reservoir serves as a central regulating storage facility, capturing water during the spring snowmelt season and redistributing it throughout the long dry months across Colorado's Front Range region. However, since the existing dam was first constructed in the 1950s, water demand across the Denver metropolitan area has increased dramatically, while the reservoir's storage capacity has remained almost unchanged. As a result, instead of building an entirely new reservoir, engineers chose a far more strategic solution, raising the height of the existing dam by 40 meters, transforming Gross Reservoir into one of the most important water storage infrastructures supporting the Denver metropolitan region in the 21st century. Before the dam could be raised by more than 40 meters, the entire load-bearing mechanism of the structure had to be fundamentally redesigned. Instead of continuing to function as a gravity dam, transferring water pressure directly down into the foundation below, the expanded upper section was engineered to operate as a thick arch dam, redirecting water loads laterally into the canyon walls on both sides. To create abutments strong enough to receive these new forces, construction teams first had to completely stabilize the dam shoulders along both sides of the valley. The work began with clearing vegetation and preparing construction access areas, followed by a large-scale drilling and controlled blasting program to remove unstable rock masses from both canyon slopes. In total, approximately 250,000 cubic yards of rock had to be excavated to expose bedrock strong enough to support the new dam structure above. In several locations, drill holes extended from the top of the dam shoulders all the way down to the canyon floor, demonstrating that the foundation preparation work was far deeper and more complex than what could be seen from the surface. On the left abutment, about 15,000 cubic yards of replacement foundation concrete were planned, all mixed directly on site to ensure strict quality control. Meanwhile, on the right abutment, engineering crews installed a dense network of rock bolts and rock anchors to stabilize the rock mass above the future foundation zone of the raised dam section. Through this reinforcement process, the two canyon walls were effectively transformed from natural terrain into integral structural components of the new load-bearing system. Only after both abutments were fully stabilized, with weak rock removed, anchors installed, and foundation treatments completed, could the project proceed to the next stage. Before any roller-compacted concrete, RCC, could be placed onto the existing dam, the entire contact surface between the old structure and the new raised section had to be carefully treated to create a continuous load transfer interface between two generations of concrete separated by more than 70 years. Unlike a completely new concrete structure, the Gross Reservoir Expansion Project requires the new RCC section to work together with the original dam as a single unified structural system. This meant the interface between the two structures could not contain weakened concrete layers, micro cracks, or weathered zones. Construction crews therefore began by removing the deteriorated surface layer using mechanical cutting equipment combined with localized drilling and breakout operations, exposing dense structural concrete to a depth of about 23 centimeters. After this initial preparation stage, engineers deployed hydro-demolition technology across approximately 18,500 square meters of the dam surface. Robotic systems positioned against the concrete structure sprayed high-pressure water jets of up to 20,000 psi, precisely removing about 7.6 centimeters of the outer concrete layer without damaging the intact structural core beneath. Unlike traditional mechanical demolition methods, which can introduce uncontrolled microcracking into still-sound concrete, hydro-demolition uses the kinetic energy of high-pressure water to selectively remove weakened material while preserving the internal aggregate structure. The result is a micro-roughened concrete surface with exposed aggregates, creating ideal conditions for strong mechanical bonding between the existing dam and the new RCC layers placed above it. After surface preparation was completed, the interface zone between the two structural bodies was further integrated into the dam's overall reinforcement system through grouting operations and foundation preparation along the crest of the existing dam. Additional drilling extended into the canyon bedrock behind the interface zone to reduce seepage and improve load transfer from the new dam section into the natural foundation. This structural interface ultimately plays a decisive role in transferring shear forces between the original dam body and the newly constructed RCC extension. The height increase of Gross Dam is being carried out using roller compacted concrete, RCC, placed in successive lifts, raising the structure by approximately 40 meters from about 104 meters to roughly 143 meters, measured from the canyon floor. Before placement began, the crest of the existing dam had to be widened by about 27 meters to provide sufficient load transfer area for the new structural section above. After removing unstable weathered rock layers, a structural foundation concrete layer was placed in the contact zone to fill small fractures and voids within the canyon bedrock, creating a continuous bonding surface for the expanded dam structure. At the same time, a foundation grouting program was carried out along the upstream abutment. Drill holes approximately 9 meters deep were installed into the canyon bedrock before cement grout was injected into microfractures to improve foundation strength and reduce seepage through the natural rock mass. Across the dam face, RCC was spread in layers about 30 centimeters thick using bulldozers, followed by heavy vibratory rollers that compacted each layer to achieve the required density and ensure bonding between successive lifts. The dam body was raised using a stepped construction configuration, with each structural step approximately 1.2 meters high and set back about 0.6 meters toward the upstream direction. In total, 118 RCC steps will form the new raised section of the dam, extending nearly 600 meters across when completed. As the structure rises, the available working width at the top gradually narrows, making material transport and equipment positioning increasingly constrained. During construction, temporary formwork systems were installed along the dam face to stabilize RCC layers until they reached their required strength. A full-scale RCC trial section, about 4.5 meters high, 15 meters wide, and more than 60 meters long, was also built on site to test construction procedures, equipment performance, and material mix design before full deployment on the main dam structure. By early September 2025, the dam had already been raised by approximately 18 meters, with about 22 meters remaining to reach its final design elevation. As the central portion of the dam continues rising in stepped RCC lifts, the structure's new form is becoming increasingly clear. What was originally a curved gravity dam is gradually transitioning into a thick arch-type structural system where water pressure is transferred laterally into the canyon walls through reinforced abutment load transfer zones on both sides of the dam. As the new dam body gradually approached the elevation of the existing structure's crest, the project entered one of the most decisive phases of the entire Gross Reservoir expansion. At this point, the RCC structure was no longer serving only as a foundation extension in front of the old dam. Instead, it began forming the new crest of the entire reservoir system for the future. At this elevation, the conveyor system transporting RCC was continuously adjusted during each stage of dam raising to ensure that materials were delivered steadily to the construction surface. At the same time, geometric control of the structure became more critical than ever because the RCC layers placed near the dam crest would directly determine the final working shape of the dam once the reservoir reached its new design water level. The final step in raising the dam involved constructing a new spillway system. The spillway walls, standing 5.5 meters, 18 feet high, were built using high-strength conventional concrete and were designed to guide and dissipate the energy of water flow when the reservoir reached its maximum operating level. Once the structure reached the design elevation of approximately 143 meters, measured from the valley floor, the new RCC dam body not only increased the reservoir's storage capacity, but also completed the transformation of the structure's operating mechanism from an original curved gravity dam into a system capable of transferring water loads more efficiently into the canyon abutments. Just as the Gross Reservoir mega construction site had completed roughly 2/3 of its total volume, and the new arch structure was gradually closing its geometry, a major legal blow struck the entire $537 million infrastructure project. The dispute began in 2018 when several environmental organizations filed a lawsuit in federal court against the United States Army Corps of Engineers, the agency that had approved the permit for Denver Water's reservoir expansion plan. The core issue of the lawsuit centered on the fact that the project would nearly triple the storage capacity of Gross Reservoir, significantly altering how water is distributed across the Colorado River system, a basin already under severe stress after years of prolonged drought. Facing the critical water needs of 1.5 million residents, Denver Water made one of the boldest infrastructure gambles in its history, moving heavy equipment into the mountains and pouring the first batch of concrete in 2022, even while the lawsuit was still unresolved in federal court. However, as the dam structure began taking shape, a recent ruling by a federal judge ordered construction to pause temporarily so the original permitting process could be fully re-examined. This means that although the new RCC dam body is steadily approaching technical completion, the future operation of the expanded reservoir still depends on the final decision of the federal court. If that decision is not overturned, the gamble could collapse entirely. And in that scenario, the $500 million structure standing high in the Rocky Mountains could become one of the most dramatic unfinished monuments in modern construction history. Solid, precise, and complete in engineering terms, yet permanently forbidden from ever holding water. And here is a little-known fact. To keep this mega project running smoothly and maintain continuous construction progress at an elevation of 2,400 meters, the entire construction site was effectively transformed into a fully self-contained industrial production system. After being mixed at the central batching plant located at the top of the site, the roller compacted concrete, RCC, was transported through a multi-level conveyor system, passing several intermediate transfer points before being released into a nearly 85-meter-high chute that delivered the material directly to the active placement zones on the dam surface. At this stage, the RCC was not dumped directly onto the lift layer. Instead, it was loaded into intermediate transport vehicles, moving laterally across the dam crest. These vehicles traveled along the placement route, turned around at the end of each lift section, and discharged the material in front of the bulldozers responsible for spreading the concrete. The bulldozers then spread each new RCC layer to a thickness of about 30 centimeters, forming the next lift of the dam body. Immediately behind them, specialized rollers followed in sequence to carry out the compaction process in 2 stages. First static rolling, then vibratory rolling until the required design density was achieved. At the top of the dam structure, the central batching plant functioned as the material heart of the entire project. Here, RCC was produced using aggregates quarried directly on site, combined with cement, fly ash, and water according to a tightly controlled mix design. One especially important component of this mixture was chilled rock, which was added during batching to reduce the concrete's temperature from the beginning, helping control hydration heat inside the massive dam structure and improving its long-term strength performance. Despite the legal ruling still hanging over the project, the massive concrete structure known as Gross Reservoir continues to rise in the Rocky Mountains like a monumental symbol of modern construction engineering. Hundreds of millions of dollars, 2 decades of planning, and the disciplined effort of hundreds of workers and engineers have been poured into this canyon, simply to repair a large-scale systemic weakness in regional water infrastructure. Engineers have achieved something remarkable by forcing a 70-year-old structure to transform itself and take on an entirely new mission. Yet at the same time, this project reveals a harsh reality. Can human engineering truly push nature beyond its limits? If the permanent restriction on filling the reservoir is never lifted, this megastructure could become one of the most dramatic reminders of how infrastructure planning can be overwhelmed by environmental pressure. Thank you for joining Mandarin Tech on this journey inside one of the most intense construction sites in modern America. Don't forget to like and subscribe so you won't miss the world's most extraordinary engineering mega projects. See you in the next episode.